So as I said yesterday, there actually is a lot more to this than what we're going to do. So those of you that are very interested in practical applications of chemistry and physics and stuff like that, this is a great example of that. So again, those of you who are interested in electrical engineering, mechanical engineering, chemical engineering, systems design engineering, whatever, will probably study electrochemical cells extensively. Okay, so we talked about redox reactions, that we want the reaction to be spontaneous. So something is going to lose electrons and be oxidized, and some other substance is going to gain electrons and be reduced. Sort of old school thinking is talking about the reducing agent and the oxidizing agent. So we're going to really focus on losing electrons is oxidation, gaining electrons is reduction. But it's so then when you do the reagent, it's like the opposite. So a reducing agent is actually the one that's oxidized because it's giving the electrons to the substance that's reduced. And then an oxidizing agent is the substance that is reduced, so it's taking the electrons from the other substance. But that's sort of, I mean, not that that's bad chemistry, it's just a little bit wordy, okay? So we're going to focus on using our table to figure out whether a substance is oxidized and which substance is reduced. So I gave you this chart. There is also a chart in your textbook. It's just very, very cluttered, okay? I like this chart. It's nice and simple. So the substance that has a higher pull on electrons will be reduced, and the substance that is going to lose electrons more easily will be oxidized. So that's what we are going to focus on. And that can help us use the chart. So maybe even your grade 10 selves, if I asked you what kind of elements gain electrons in a very, very general sense, what kind of elements gain electrons? Good. Write that down. Okay, so then in grade 11, we spent more time on trends, that the tendency to pull electrons towards itself, like increased up and to the right, towards fluorine. Fluorine, we said, was the most reactive nonmetal because it was small and had a very attractive nucleus, all that kind of stuff. But even if you look at this chart, at the very top, the topmost top, is fluorine, okay, which is a nonmetal. So if fluorine is the most electronegative element, then its capacity to gain electrons is going to be great. Okay, so what type of elements would we say lose electrons then? Good. So then again, that would be maybe grade 9, but for sure grade 10. In grade 11, with the trends, we talked about the alkali metals, how reactive they are because they only have to lose one electron. But even if you forget that, at the very bottom is lithium. Which is an alkali metal, super reactive. Okay, so then if it's closer to the top of the chart, it's going to be reduced. And closer to the bottom will then be oxidized. So this is important. But you can use the patterns we just talked about. So fluorine's at the top. Fluorine is a nonmetal. Nonmetals gain electrons, okay? Which is reduced, Gur. Yes. Now, sometimes there are other nonmetals on here. Sometimes you will be comparing metals and nonmetals, but sometimes you will be comparing metals themselves. So again, a redox, writing a redox reaction, considering what a redox reaction is a little bit better, a little bit more, we don't have to skip questions. We can compare even the same type of element, okay? So that's an advantage. And then what we're going to do, we're going to take a look at what this value means and how that can help us decide if our battery is going to spontaneously work, which is, of course, what you would want, right? So the only thing that's strange about this that you really have to be careful about, so if you take a look, so this is copper 1, and this is why I like this chart better. If you can imagine your textbook chart being even more crazy and confusing and cluttered. So look on yours, don't look on mine, but this says Cu plus to copper solid. This says Cu2 plus to copper solid. So you do need to make sure when we actually use the electron volt value that you use the correct form. So this isn't a typo, okay? There is a version that's Cu2 plus, okay? But so these two are right on top of each other. I don't usually do that. Usually it's very far apart. So copper 1 to copper solid is right here. And then iron 3 plus to iron 2 plus. Oh, I lied. This is really close together. Okay, that's nasty. I try not to do stuff like that. Okay? So which one is higher on the chart? It's the iron. So this is reduced. Copper is lower, so it's oxidized. Chlorine. So chlorine, now we have, this is a bit of an easier situation, right? This is a nonmetal. So in your head, you're already thinking, okay, then it probably should be reduced. It should gain electrons, but let's check. So chlorine is way up here, and then silver 1, sorry, to silver solid is much lower. So this is oxidized. And this, oops, sorry. So this is, you could almost answer it and then check with the table. So this will be included as part of the reference information for the exam. And I'm going to use this version because it doesn't, when you look, if you look in your textbook on page 805, you'll see like it's just crazy. Too many things together. This is much easier to read. All of these are called half reactions. They're all written as gaining electrons. That's just the way the standard chart is formed. That doesn't mean that they are all going to be reduced. Remember, oxidation and reduction has to occur simultaneously. So if something is oxidized, then another substance has to be reduced. Okay, so this type of question, I'm going to show you how to combine reactions and write a redox reaction. But this isn't going to be on the exam, but that's okay. I'll show you how to do it just in case you have to take first year chemistry. So a half reaction, and that's what these are. So all of these are only showing 1/2 of the reaction. We need an oxidation as well. So all the half reactions in the standard table are written as reduction. So then you would have to rewrite whichever one's oxidized with the electrons on the product side. Okay, so write and label 2 balanced half reactions to describe the reaction of zinc metal and lead nitrate. Okay, so in here we have zinc solid changing to zinc aqueous, lead aqueous changing to lead solid. Nitrate is aqueous on both sides, so what do we call that? What kind of ion is that? Yes. So if you go to look on the table, there is no nitrate because it's a very common spectator ion. So again, if you remember from grade 11, often we use nitrate as a substance in our aqueous solutions because it's soluble in everything, with everything. Okay, so we have zinc and lead. I'm just going to go back to my table for a second. Okay, so we have lead is down here. And, zinc must even be lower because I cut it off. Yes, zinc is way down here. Okay, so lead is reduced because it's way higher. It's almost in the middle, right under the 0. And then zinc is way down here. Okay, so the one that is reduced makes your life easier. All you have to do is look at the chart and copy it out. And we are still following this same principle. Gains electrons is reduction. So the lead ion is gaining electrons, which is reduction. So then we said that zinc is oxidized. So all you have to do is flip it around. You can decide if you would like it to actually be sort of like a Hess log question where we lined up the arrows. You decide. Okay, so on my chart, zinc looks like this almost, except it says zinc 2+ plus 2e. I don't want it to look like that because it's not it's not reduced. So you have to flip it. So then if you had to write the overall reaction, you would cross out the electrons. We don't usually consider those to be chemical substances. So we have ions, lead ions plus zinc solid. The zinc is going to lose electrons. The lead ions gain it to become a solid, which leaves zinc as aqueous ions. Okay, so you're going to have to do this part. Which one is oxidized? And which one's reduced? And then you're going to use that information to calculate the voltage supplied by this reaction, which theoretically could then be a battery if the reaction is spontaneous. And then to calculate that, this is given on the reference sheet. So take a look at the exam review, it's on there. And then you have to say if the standard energy or the standard voltage is greater than 0 or positive, then the reaction is spontaneous as written, the net reaction, and if it's not, then it's not spontaneous and you couldn't use that as a battery. So in order to figure out which one's reduced and which one's oxidized, you have to use the chart. So this part of it, you're going to have to do, we said lead is reduced and zinc is oxidized. I don't know why that F's there. That's all right. Okay, so lead's value is negative 0.13. The unit is given at the top, but it's voltage, like a battery, like electricity, unit of electricity. Then zinc is negative 0.76. So negative 0.13 minus negative 0.76 is 0.63. Is that positive? So the reaction is spontaneous. Okay. a little star around that. Mm-hmm. Okay, so then what you would do is look at what a battery would look like. Okay, so initially, and there's actually sometimes these batteries or electrochemical cells are called by the people who studied them. A Daniel cell, Volta was a person. So these reactions were obviously very useful. Obviously, as human beings, we use electricity and batteries all the time, right? So a galvanic cell is a cell that's going to be spontaneous. This is usually what chemistry focuses on. Should you take physics or engineering, they switch the focus more to electrolytic cells, which are essentially rechargeable. So you plug something in to give energy to drive a non-spontaneous reaction. So the energy sort of becomes stored in the reaction. And then when you unplug it, then that energy can be released and you can take your laptop, iPad, cell phone, wherever you want until that battery runs out and you have to recharge it again. Okay, so this is an example of what a very rudimentary electrochemical cell would look like. Obviously, in your laptop, whatever, you don't have beakers with metal electrodes like that, but you do have a plus and a minus on a battery. They do have to be, the orientation is important when you put it in your machine. It also does have solution inside of it, which can then, if it's punctured, it can leak out, which is dangerous. So even though this is really basic, it's still sort of modified to be a little bit more mobile, but still the general principles are the same. So we have a solution that's providing spectator ions that don't come to the event. They're just there to sort of make sure that the buildup of what you don't want is minimized. There is a point where it just peters out, right? No more electricity can be generated in a battery and you have to dispose of it. But we try our best. And then one of them has to be reduction and one of them has to be oxidation. And another, again, sort of more physics idea is that, does it say it on here? That the cathode is another term for the part of the battery where reduction occurs, and anode is oxidation. And then in physics, they focus more on the cathode being positive or negative, anode being positive or negative. There are different situations where that occurs, but that's sort of not what we need, at least in grade 12. Okay, so we want putting them together, we want it to make measurable energy. So if you remember in grade 9, you would have had a little voltmeter and you attached it with alligator clips to all kinds of things. Probably you did those snap kits, hopefully. So then you want electricity to be produced spontaneously. So zinc, whichever one's lower on the chart, in this case is zinc, will be oxidized. The zinc loses electrons. And as the zinc loses electrons, the solid is going to be turned into ions. And this piece of metal would actually get smaller and smaller and smaller until, again, it ran out and the battery would die. then the copper is higher on the chart, so it's going to be reduced. So the copper is going to gain electrons and get fatter and fatter and fatter, again, until it can't hold anymore and the battery dies, okay? So inside a battery is substances that really shouldn't go in the garbage straight up to an ecosystem. Okay, so this question, there's two of them, is I included this is called cell notation, okay? But it really is sort of the same thing as writing the half reactions. We're going to decide which substance is oxidized and which substance is reduced. Then I took this off the exam, but once because it's sort of memorizing, cathode is reduction, anode is oxidation, and then we're going to calculate the standard cell potential and state whether the reaction is spontaneous. So the way I formatted your sheet, if you would like, there's a column here and a column here, like you can go down to do each equation, okay? So there are people who will be really, 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 like professors or whatever, will be really strict about how you do your cell notation, but it really, like your textbook versus if you happen to be, a Googler, then they actually, a lot of the sites that I was just curious, they actually did it backwards, but your textbook wants oxidation first and then reduction second, but that doesn't matter. What you're going to do is use the chart, okay? So zinc and zinc 2 plus, is that higher or lower? Than copper, okay? So we're going to that's what we're going to do. So don't worry too much about this cell notation. Just worry about how to use this, okay? So whether you get a little bit confused and do copper 1, copper 2, copper 2 to copper 1, they're actually all sort of in the same spot, and zinc is way, 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 way below it. So copper is definitely higher on the chart than zinc, so that means that zinc is oxidized and copper is reduced. Okay, so again, this is a memorization thing, so I took it off, but the cathode is reduction, which is copper. Anode is oxidation, so that's zinc. Okay, but the third part we have to do, so again, I'm just going to flip for 1 second. The equation is given to you. Look up the value for reduction and subtract the value for oxidation. So when you do this, when you decide which is oxidized and which is reduced, again, it's one of those situations where it's 50-50, make your best guess and then keep going, okay? Because you're going to be given this. So whatever you've decided is reduced, use that value. Whatever you've decided is oxidation, use that value, okay? So copper 2 plus to copper solid is 0.34. You okay? And then zinc is negative 0.76. Again, remember the positive part is what tells us whether the reaction's spontaneous or not. So if the value's negative, keep the negative. If the value's positive, keep the positive, okay? So 0.34 minus negative 0.76 is 1.1. Is that spontaneous? Yes, because it's positive, and it's much more positive than the other reaction. So, and a further step to this, not that we have to do this year, is to say, okay, this might actually be a better battery because the voltage is greater. Okay? Bless you. Okay, and then the last one, not that I was trying to be sneaky, but again, just to get used to using the chart, there are different oxidation numbers for transition metals, so just make sure you're looking at the right one, okay? So silver only has one charge. That's a little bit easier. But this one, I chose not the solid form on purpose, okay? Not to be nasty, just to make sure, you know, that you're trying your best to get the right value. Now, to be honest, if you wrote this down and showed me your work and, you know, I could figure out what you had done, then I can give you more marks. If you just put down a value and I don't know where you got it from or whatever, then that's a little bit trickier. So silver solid is pretty close, like a little bit, you know, I don't know, like a quarter of the way down. And then Fe 3 plus and Fe 2 plus is below it. So this is reduced because it's higher, oxidized because it's lower. So this is the cathode, anode, Okay, so is this reaction spontaneous? Yes. Is this a terrible choice for a battery? Also yes. That is a tiny amount. So that's why usually the questions, the values are much farther apart. That generally makes for a better reaction, okay? To produce a greater amount of electricity more spontaneously.